Hey guys, your boy Chili here. Welcome back to STD Gems. Today we're going to be looking at the heap operations in the standard algorithms library. Now, you hear the word heap, you're going to think, I know this stuff. It's all about, new and delete and malloc. It's all about memory allocation. No, there is a bit of a naming problem. If you haven't been aware, some naming problems in C and C++. We're all aware std vector is a terrible name for what the thing actually is. And the name that has been given to the dynamic memory allocation storage class or region known as the heap is a bad name because a heap originally has a meaning in computer science and structures and algorithms, and it has nothing to do with the heap of memory allocations. So put that out of your mind. This has nothing to do with that. Now, what a heap is it is a data structure that has a few very nice properties. One of the good properties is that the top of the heap is always going to be the largest or the smallest value, depending on what kind of heap it is. Insertion into the heap that maintains this property is a log n operation, and removal from the heap, removal of the largest or the smallest element from the heap, is also going to be a log n operation. It turns out these properties are very nice in certain applications, but before we actually look at the functions from the standard library here, let's take a little deeper look into what a heap is and how it works. So again, we'll check out our data structure visualizations. If we go down here, there's a whole section on heap-like data structures, all sorts of different types of heaps. We're just going to go for the vanilla heaps. All right, so what do we got here? It looks like an array. But let me tell you here, heap is actually visualized and conceptualized as a tree. So let's just try it out. Let's just try inserting some values into our heap here. And we'll go 29. Insert that bad boy. All right, so we've got our root node is a 29. Let's insert a, this is a min heap, by the way, so it's going to try to keep the smallest element up here. So let's try and insert another value. Well, let's try and insert a larger value, 34. Insert. That one goes here. Okay, it's starting to look a little bit like a tree. Right now it's a linked list, but if we insert another one, let's go 33. Insert that one. And it goes on the right side here. Okay, so we're building a kind of a tree. You can imagine if we inserted another one, it's going to probably be, a child of, one of these guys. So let's try and insert and now a value that's smaller than 29. See what happens. Let's go with 20. I'm going to turn down the animation speed by a lot here. So we insert, it goes here. Then we swap, then we swap. All right, so now we're starting to see a few things. So first of all, you're going to notice when you insert into the heap, it's very regular where the new element starts out. It fills top to bottom, left to right. So we fill this one, then here and here, then here, 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 here. It's very regular. So you'll never have a tree where one end is much longer than the other, which is a thing that you have, with your basic binary trees. Now, the second thing you notice is after you've inserted a value, it's going to do a comparison with the parent and see, is this smaller than the parent? And if so, it's going to swap. And it's going to keep doing that until it is no longer smaller than the parent. So if we try to insert a 17, I'm going to turn the speed way down here. Insert a 17 into here. It's going to go into the next place. It's going to compare and swap and compare and swap. What if we tried to insert a value now that isn't smaller than 17, but is larger than 33, which is going to be the parent of the next node? Well, we could try inserting a 31 into here. And it is going to go into here. It's going to compare and swap. It's going to compare, but no swap. It stops here. And it's this behavior that maintains the smallest element at the root here. Another very neat property of heaps is that we visualize it as a tree. So this one here, this is a heap. But the children nodes of this root node are also trees, and they are also heaps. So in this child tree of the root, this is going to be the smallest element of the whole, the smallest element of the whole child tree. Let me just insert a bunch more values and you'll see. So you can see here in this subtree here, 16 is smaller than any of the other values in here. So this forms a heap. You see 20 here is smaller than 34 and 32. 17 is smaller than 29 and 23. So subtrees of a heap are also a heap. Now, after observing how a heap works, it's not too difficult to see why we get the log n complexity for insertion and removal. The number of elements is going to be basically 2 to the power of d, where d is the depth of the tree. So the number n is equal to 2 to the power of d, that's exponential. But the number of swaps you have to do is on the order of d. So the relationship is n is equal to 2 to the power of d. We know insertion and deletion is going to be about linear in d. So to write that in terms of n, we take the log of both sides. By the rules of logarithms, we can take this exponential inside and pull it out into a factor outside of the log. And then we just know that log 2 of 2 just simplifies to 1. So we're left with d is proportional to log of n. Now you see our operations are on the order of log n. Now you might be wondering to yourself, why would we do all this complicated stuff? Why not just maintain a sorted range, just a list or vector that is sorted from smallest to largest? Then we know the smallest one is always going to be at the beginning. When we insert, we just have to find the insertion point. We could do that with a binary search and insert in there. But the thing is, that's actually not going to be log n for insertion. It's going to be n, because after you find the insertion point and you insert, you have to shift all of your elements over, and that shifting will give you big O of n. Whereas in a heap, at most, you're going to be shifting d times, where d is the depth of the tree. And so if you're only really interested in getting the smallest, or for a max heap, the largest element out at any time, then a heap is going to be much more efficient than a sorted range. Now finally, let's take a look at what happens when you want to remove the smallest element of a min heap. Because you can't just remove it and do nothing because you've broken your heap. You have to reconfigure and figure out which is going to be your new smallest element. So when we remove smallest, we're going to remove that element there. We're going to take the back of the heap and we're going to put it up here. And then we're going to do the opposite. We're going to push down the heap. So remember, the heap always grows very regular. So when you add a new element, it's always going to go in the same position, and then swaps are going to happen to refix it. Same thing when you remove, it's going to pull one off here, put it up into the root, and then try to push it down. Where's the next one going to be pulled away from? Well, it's going to be pulled away from here, right? So if we remove another one, 31 is going to go up here, and then they're going to try to push it down again. So here goes 31, and it's going to compare both of these and push it down to the smaller one because it wants the smaller one up here. So it has to actually compare two. It has to compare this one and then go to the smaller one. So we can see here that removing is generally going to be 2 times more expensive than inserting, but it's still both a log n operation. Now, at this point, you might be saying, well, that's great and all chilly, but where am I actually going to use this stuff? And it's actually quite useful. This allows us to build what is known as a priority queue. And priority queue is useful in many ways in games or other places. Imagine a system where you've got like an RPG, a bunch of characters are taking actions. So they choose their action, and the actions have different delays. Some things have to charge up. So if player A and B both choose actions, first player A puts an action on the queue, player B puts an action on the queue, they might not happen in that order. It depends on how much delay is in all those different actions. But if you have a priority queue, you can insert items into the queue in any order you want, but then pull them off in the order of smallest to largest. Another thing that requires priority queue is the A-star pathing algorithm. It's a graph search used for pathing in many games, and it requires a priority queue. Another thing, a very common sorting function, heap sort, it also relies obviously on heaps. Now, another beautiful property of heaps is because they grow so regularly and shrink so regularly, and the positions of each of these nodes is very regular. Although we visualize them as a tree, you don't have to store them as a tree. You can store them as a vector, as you can see is happening up here. And it's very simple how you do that. Like, let's say you take this node here. The root is at 1. So its first child is going to be the one that comes right after, and then the second child is going to be the one that comes after that one. And then the first child of that one is going to come here, right? It's all just very regular. You go from top to bottom, left to right, and that's the order it comes in the vector. And if you want to find the child of any given node, all you got to do in this case here, we're 1 based, it's very simple. You just multiply by 2. So this one's first child is its own index times 2. Second child is index times 2 plus 1. Let's look at a more complicated example here. This one here, 28. What's its first child? Well, that's going to be, let's find it in here. So 28 has an index of 6. We want to find its first child. We multiply by 2. 6 times 2 is 12. It should be 41. We look down here. Yeah, it's 41. Pretty damn easy. And its second child is just going to be 6 times 2 plus 1, which is 13. And yeah, that's 33. And if you want to go the other way, if you want to find the parent of 33, you just do integer division by 2. So 13 divided by 2, integer division is going to be 6. And there you go. You found the parent. So it's easy mapping. It's a little annoying to do manually, but hey, that's what the standard library comes in. All right, now let's look at the actual functions in the standard algorithm library. We got push heap and pop heap, and those represent those operations that have been demonstrated already, but probably easiest to start with make heap. All you do is you give it a range of elements, and it will turn that range into a heap. So we got a very simple setup here. We generate a vector, has 20 elements, randomly selected values between 0 and 99. We write out the vector, then we call make heap on it, and we write it out again. So here we have the random sequence, and then we have the sequence after it's been turned into a heap, after it's been heapified. And so first thing you notice here, and you could see that from the description of the functions, but make heap will by default make a max heap. So the first element will be the largest in the container. The next two are going to be obviously smaller than that one, 92 and 93. And then the children of 92, 83 and 80 are smaller than 92, and so on and so forth. So you can inspect this and see that it is indeed a max heap, which matches the description right here. Now, what if you wanted to make a min heap? Well, it also takes a comparator, and just like for sorting, if you want to do it in the opposite way, you just got to give it the other operator. So this one uses the first version uses operator less. So if we give it greater, then it should give us a min heap. So we go std greater. I don't know why my IntelliSense hates me, but it doesn't want to find that. But anyways, template that on int, create the structure. And now we've got a functor that should give us a min heap. And now we have a min heap. Now isHeap is super simple. You give it a range. It tells you, is that a heap or not? Is it a valid heap? And we'll return a bool for that. isHeap until, a little more complicated, but you just give it a range and it will scan through that range and it will tell you the point at which there is an element that fails to satisfy the heap requirement. So here we can, call isHeap on this bad boy. It's going to return false. Why? Well, because we make it as a min heap here, but we're not testing it as a min heap. So let's make it a max heap. Now it returns true. Okay, so far so good. Now, isHeap until will return an iterator basically to the first element that poisons the soup. So let's turn this thing into a heap, but then we're going to set element 10 equal to 100. So since this is a max heap, if there's a value of 100, that should be at the beginning because the other values are only from 0 to 99. So when it encounters this one, it is definitely going to say, what the hell, this is dumb, and that should be our heap end. So let's see the distance. So the distance, I guess it should be 10. My arithmetic is working out correctly. Yeah, 10. So you can test for heapness or see up until what point a sequence is a heap. Might be useful. Maybe you have, from frame to frame, you have stuff that might mess the heap up and you just want to see how much you have to fix up or something. I don't know, but it's there. One last thing to note, you could make a heap by just calling push heap one element after another, but it's actually faster to call make heap all at once over an entire range. It's linear, whereas if you were to call push heap n times, that would be n log n. Now push heap and pop heap are probably the most important functions in here, and they're a little complicated, but not that bad. So give them a range, and it's going to insert the element at position last -1 into the max heap defined by the range first to last -1. So might seem a little weird. What is that? Basically, let's say you've got a vector, 4 elements, and these 4 elements are arranged as a heap, and you want to push something into this heap. So what you would do is you would first push a value to the end of this vector. This value is currently not part of the heap. It could be anything. Then you call push heap on this entire range, and it will rearrange it so that this range now, the full range, becomes a heap. So when you call push heap, the range that you call it on, the last element could be just any value, but the rest of the elements here have to form a heap. That's what that is saying. So let's push a value onto our heap. The first step, like I said, is you have to push the value to the back of the container. So we'll get a nice value in there. And then you call push heap. And we pass it the full range of the container now, which contains the heap plus the non-heap value at the end. And then we're going to print that out. So here we are before we push. Then we're going to append a 420 to the end and call push heap, and it is going to propagate that up to the top because it is the largest value. So not super complicated, but it is a 2-step process. Now pop heap basically does the inverse of that. So it's going to swap the first element, which is the top of the heap. It's going to swap that to the back, and so the back is going to come to the front, and then it's going to re-heapify everything but the last element, which is the element that you want to pop off the heap. So imagine you've got a vector of 5 elements here. They're arranged as a heap. You call pop heap on this boy. What's it going to do? Well, it's going to swap the front and the back. So now because these are swapped, these elements no longer, they are standing out as not heapified. They are not in the correct places if this was to form a heap. Then what the algorithm does is it re-heapifies this section. So it might have to push this one down a little bit, and this one remains at the end, which you can then retrieve and, possibly pop back. Technically, you could, retrieve the top of the heap. You could copy it out before or after the pop, because either way, they're very easily accessed. Let's retrieve it before we pop. So we can go, auto top is equal to a dot front. That's the top of the heap. Then we can do std pop heap, and we'll do it over the entire range. Now the back of the heap contains the value that has been popped off, the old top of the heap. So let's go a dot pop back, remove that, and let's print out the result. And that'll look something like this. And then when we run it, we see top of the heap becomes 98. Then when we pop off, that gets removed from the heap, and 98 has been removed from the heap there. Then we're going to push 420 onto the heap. There you go. We check it's still true. And when we set element 10 to 100, the heap becomes valid up until element 10. There you have it. There are the main operations for heaps. Now, something interesting that we can note here. If you got a heap, 5 elements, and you pop back, it's going to swap. It's going to remake this one, and the end is no longer going to be part of the heap. It's going to be the old largest element. If you were then to pop on the range that's remaining, the remaining heap, you get the next smallest element, or the next largest, and then the next largest. So if you were to recursively, or loopily do that, what do you end up with? Well, let's try it out. Let's create a loop here. We're going to go for auto first is equal to a dot begin, and last is equal to a dot end. And as long as first is not equal to last, I'm going to do last minus minus, or maybe minus minus last. Yeah. All right. So we're going to loop, and we're going to be bringing in the last. It's going to start on the right, and we're going to bring it down towards the left. So let's print out the range that we have, and then we're going to do std pop heap first, last. So we'll pop that, and then last will be pulled in by 1. So last will, at the end here, last will always be adjusted to the range of the valid heap after the pop operation, and then we'll pop another one off. And then at the end, we'll write the result. So if we run this, no, I guess it's probably a good idea if we're going to be using pop heap to actually turn it into a heap before we start. Might help things out just a little bit. Okay. All right, let's run this. So we get our random distribution. It's been turned into a heap. Here's the largest value. Then we pop heap. So the largest value goes to the back. So the new largest value is going to be 87. We pop that. Pop, 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 pop. And what do you get? At the end, you're going to get a nicely sorted sequence from smallest to largest. And that, my friends, is what heap sort is. You make a heap, and then you just pop off the heap until you have a sorted sequence. And you can see finally here, standard library has sort heap, which does exactly that. Very simple. You can look here, the implementation is dirt simple, just keeps popping heap over the whole sequence. So we could replace all this stuff here with std sort heap like this, and you will see it does the exact same thing. Obviously sequence is different because it was random, but here we see it has been sorted now. And there you go. So there's a very easy way to make a sorting algorithm. They tell you you have to implement a sorting algorithm using standard C++, but you can't use std sort. Here you go. But there you have it. There is the heap operations. And it's not the most difficult to understand data structure, but it's a little more interesting than, like a sorted range binary search sort of thing. So it's getting a little more computer sciencey in there. And these operations are not too difficult to manage, but it's a little annoying. You have to do, if you want to push something onto a heap, it's a two-step process. And there's actually something in the standard library that makes this much sexier. And that's a little teaser for you guys. In the next video, we are going to be taking a one tutorial detour from the algorithm library. Gonna check out something that is related to heap operations, and that is gonna make things like the priority queue much sexier. Until then, hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more STD gems.